So now that we've talked about the structure and functionality of the ImageStreamGang program, let's visualize its behavior before we start diving into the code analysis. And this is always kind of fun because I love to look at things visually. And we'll see how this is going to be used, and we'll talk about how this works under the hood. Now, there's another program I wrote a long, long time ago called the ImageTaskGang application. And the way it's designed is using earlier Java 5 level concurrency mechanisms like executor service, executor completion service, and so on. And this solution we have here is much cooler and better because it uses the streams version. But there's another version if you want to see how to do older styles of Java concurrent programming if you're so inclined. So as we talked about earlier, this app uses a parallel stream with blocking I/O. And that's very important, as we just talked about, because that means that it's an I/O-bound processing for the most part. There, of course, is computation stuff, too, when we do the image transforms. But there's time spent sucking the images down from the web, and then there's also time writing the images to disk. So that's I/O computation. And as we'll see, we combine object-oriented and functional programming features here. The first thing that we do is we're going to ignore any images in our list that have already been downloaded and processed, just because why duplicate that? And it also gave me a good excuse to use the filter operation. So we want to filter out stuff that's already been seen. For stuff that's not been cached, we want to download those images. And so that's, of course, going to end up using threads in the common fork join pool for the parallel streams version. And after we've downloaded the images, we can do various things. We could store the images on disk. We could put the images in a hash map. This particular implementation stores them on disk. And then we go ahead and we take a list of filters, not the filter operations in Java streams, but I should probably call them the list of transforms. And we have the list of filters to apply to transform the images based on whatever the transform algorithms are. So it could be a tint filter or a grayscale filter or a sepia filter or an emboss filter or whatever your favorite filter is. And then the final thing we do is we store the results of the images on the file system. So downloading is going to be I/O bound. Storing the images on the file system after they've been filtered will be I/O bound. Actually, storing the original images on the file system will be I/O bound. And then applying the filters to the images, that's not going to be I/O bound. That's going to be computation bound. And then the final thing we do is we actually display the images to the user based on what computations they've done. And it's kind of cool. If you look at the Android version, that's the app version as opposed to the command line version, it has a separate activity that's kind of like a gallery where you can give it a place on the disk to find the images, and it'll go ahead and display them. So that's a neat use of Android activities. Internally, the app uses a parallel stream with blocking I/O, and these are the steps that are involved. And what's cool about this is that the pipeline of processing you see here is pretty much one-to-one with the description of what we're doing. So the way I like to say that is the intent or the requirements, which is kind of this statement on the left, is almost one-to-one with how we represent the solution on the right. And I won't go through the painful process of showing you a non-object-oriented solution to this, or rather a non-functional solution to this, but it would be much more full of low-level imperative details that would blind you or disguise the actual mapping onto the specification of what's intended. So this is a nice way of kind of combining this. So you can see we ignore cached images. That's the filter step. We download the images that were not cached. That's the download step. We apply the filters. That's the apply filter. And we also combine that with storing them to the file system using the decorator pattern. And then we collect the results and we display those things. So it's nice because it's very high level. And what I like to say, the way I phrase this, is it closes the gap that otherwise exists between the so-called domain intent, which is all this stuff here, the list of bullets that we're doing, and the computations that actually implement this domain intent. So what you're seeing here is we're applying functional programming features like lambda expressions and method references and functional interfaces and streams and so on in order to make the programming look a lot more like what we're trying to do, as opposed to having our list of things to do and then having our program written in a very low-level imperative way. So this is kind of what it looks like visually. So we take a list of URLs and we turn it into a parallel stream. And as we've talked about before, what will actually happen there is we'll have this pool of threads, and each URL will be pulled through all the operations from the source, which is the list of URLs initially, which have been turned into a stream. So parallel stream converts the list, the collection, into a parallel stream. We then output a stream of image URLs. So again, keep in mind, this is not actually going left to right. This is going top to bottom. But effectively, it's as though we have a transformation of the list of URLs to a stream of URLs. Then we have the filter operation, which is given the stream of image URLs, and it will ignore the images that are already cached. We output a stream of non-cached image URLs. So now there could be fewer of them, as you see on the left. We then apply the map operation, which takes the stream of non-cached image URLs and downloads them. And of course, this will all take place in parallel because each of these threads in the common fork join pool is going to run in parallel on the different images in the stream that it's dealing with. And what we get from that will be a stream of downloaded images. So now we're moving from a stream of URLs, which I represent by the little gray squares, into a stream of images, which I represent as the little gold circles. Then we go ahead and take that stream of downloaded images and we connect it to map. And that will then go ahead and apply another method reference, which is the apply filters method. And that will apply the filters to each image in parallel, because it's all a parallel stream, of course. And as those filters are applied, the images will be stored in the file system. So what we end up with there is a stream of images that have been transformed, hence the different colors, trying to visualize it. And let's say, for sake of argument, that the sort of lavender color is the grayscale filter, and the little blue color is the sepia filter, or whatever. But you get the point. For every image that was downloaded, we're going to end up with k copies of that image that have been transformed. So we take the image, we transform it, we store it. So now we have a stream of streams of filtered and stored images. And there's some other stuff that I've left out of here just because it would make the slide too complicated. But what we really do in practice is we do the reduce operation, and that ends up basically letting these things all run in parallel. And the final thing we do is we collect all the results into a list. So we end up with a stream of filtered and stored images as the result. And so that's what it looks like visually. And again, keep in mind, it's pulling those operations through each of the phases in the stream. Of course, nothing starts to run until the intermediate operations are hit, and the terminal operations are hit. That's what starts everything in motion, and everything runs at that point. So we end up with a list of filtered and stored images from collect. The cool part about this is that the Java Streams framework orchestrates all of this stuff in parallel. You don't have to know, you don't have to care how it works. It's doing it all on your behalf. And the other nice thing is, if we want to start by writing our program to be sequential, maybe it's easier to debug, for example, all we have to do is change parallel stream to stream. Nothing else changes. Now it works sequentially, and maybe it's easier to debug because there's only one thread of control, so you can set breakpoints and make better sense of what's happening. So it's really cool and really easy to switch back and forth between non-concurrent with sequential approaches and concurrent or parallel approaches with just a flick of the switch. And you've even seen that in your programming assignments where you can actually do that conditionally. You can have, parallel ? List.parallelstream, otherwise list.stream. And so you can make those decisions in a very late binding way. All right, so that's the end of the overview of visualizing the ImageStreamGang case study in the case of parallel programming.